welcome to this new inTechBrew webinar. I'm Xavier Poteau from inTechBrew, and I will be your host for the next hour. Today, we will be talking about some of the latest solution in nuclear measurement with CAEN SyS and CAEN Scientific joining us as well. For those of you who don't know anything about CAEN, and I'm sure they will tell you a lot more about that, CAEN SyS is based in Italy, is a well-known company for their innovative radiation detection instrumentation. And with the help of CAEN Scientific here today, one of their distributor in the UK, the next hour promises to be very interesting. But before we just start up, here's a few words about inTechBrew. So inTechBrew is a digital platform with a focus on innovation for the nuclear industry. Our main mission is to help hidden gems be more visible. We access the best technology and fit-for-purpose technologies from across the world, and we showcase them through inTechBrew. And we only select technology independently through our expertise. Next slide, please. So if you join the inTechBrew community, you get access to innovation from a wide range of topics, a database of the best innovation we scouted worldwide, and very detailed view of each technology with user cases, specification, and insight. Every 2 months, it's 5 new technology, and you also get access to all the back issues we ever done over the last 2 years we've been existing. Next slide. So if you subscribe, as I said, to inTechBrew, you can re-engage the workforce with innovation and do like the community who's already following us. And you can see some examples inTechBrew. Now for the main event, I'm very happy again to have CAEN SyS with us today to talk about radiation detection. Just before we start, just one little reminder, there will be a Q&A session towards the end of the webinar. How this will work, we'll be taking questions from you through the chat function of Teams. All right, so during the presentation, if you have a question, just pop it on the chat and we will select as many as we can and cover as many as we can before the end of this webinar. Right, now for this great session, we have today 3 presenters, Yuri, Giacomo, and Aftab. Thanks a lot for joining us today, guys. I will leave you to tell us more about yourself and CAEN SyS. Yuri, are you okay to go?
Yeah, we are ready, and you should hear us. Just confirm that you can hear us very well.
I can hear you perfectly. The floor is yours.
Okay, thank you very much. And first of all, let me say a big thank you to Axel and Xavier and the inTechBrew team for inviting us in this webinar, and thank you to all the attendees for taking the time to attend as well. I will just give a brief introduction of the company, and I will give a pitch of what CAEN SyS does and what is our mission. CAEN SyS, as Xavier just introduced, is the system and spectroscopy division of CAEN S.p.A. CAEN is recognized as a leading technology provider in the field of nuclear and particle physics, and now this expertise is available for the radiation detection and the nuclear industry sector. So the SyS team is addressing the industrial nuclear field and is developing instrumentation technologies in the areas of fuel cycle, reactors, security, safeguards, and many other applications. Our mission is to provide our customer with innovative radiation detectors that are adding operational benefits and are enhancing security and safety. In our portfolio, we have instruments fixed and portable for gamma and neutron detection and identification, tailored for different applications like environmental radiometry and spectroscopy, homeland security, safeguards, and others. In CAEN SyS, we have a team of electronic and software engineers that are dedicated to the R&D of these products. We have a group of physicists and nuclear engineers that are making customer support, and they are managing the product life. And we also have specialized technicians that can do on-site support and installations. That is a great plus for us. As you can see in this slide, we have a worldwide presence thanks to a network of authorized distributors worldwide. Moreover, we maintain 4 headquarters around the globe, in Italy, where we are based, in the US, in Germany, and recently also in India. As a representative of our resellers, today with us is Casey Scientific with their managing director, Aftab Quadri, who will give in a minute just a pitch of the activities that they are carrying on in the UK. This is just an overview of our key accounts, our main customers, among which you can see we have the US Department of Energy, the IAEA, and many others. So thanks to our network, we can collaborate with these foreign authorities in an efficient way. Let me also mention that we are involved in R&D projects with the goal to continue developing our expertise in high-level electronic design. And among the most important, we have the Mikado project that aims at building a new reference standard for nuclear waste management, and Silent Border, which is another project to explore security applications at borders and customs. And on the next slide, here is the team that is available to you today. We are ready to assist you during the webinar. So I let Aftab just give a pitch of the activities in the UK as a local reseller, and then we give the floor to Giacomo for the technical presentation today. Thank you all very much.
Okay, good afternoon, everybody, and thank you for the introduction, Yuri. I hope everyone can hear me. I'm not very good at Teams, but yeah, I would just like to quickly confirm that Casey Scientific have the full range of CAEN's, not only their nuclear physics instrumentation, but also the CAEN SyS radiation detection and measurement systems, including the Sniper GM, which Yuri and Giacomo will preview in this webinar today. And all these products are available from Casey Scientific in the UK. Our customer base in the UK is solely focused on the nuclear sector and the R&D sector, which includes universities and most of the nuclear and physics, particle physics type laboratories in the UK. And I would welcome any inquiries that you have for any CAEN or CAEN SyS products, and look forward to dealing with you in the future. Thank you, Yuri, for that introduction. If I can pass you back.
Okay, so thank you, Yuri. Thank you, Aftab, and thank you to the staff of inTechBrew. I'm Giacomo Mangiagalli. I'm a CBRM product specialist. I'm in charge of the technical introduction for the products of CAEN SyS division. And as my colleague just said, today we are going to introduce you the portfolio of the radiological and nuclear security products. So the product that we design, realize, and distribute for homeland security application, ranging from really small device like handheld up to vehicle mountable system, with a big focus with the, let's say, most special device that is the Sniper GM, that has a special feature that I'm going to introduce during the webinar. So let's start with the webinar topic. I give you just a brief introduction of the theme of this webinar. So I was talking about radiological and nuclear in the framework of CBRNE, that is chemical, biological, radiological, and nuclear explosive. We deal with radiological and nuclear mainly. And nuclear emergency are categorized by the IAEA in 3 main categories, depending on their on-site and off-site threats. So it depends on the scale of the accident, let me say, in a simple way. And these category 1, 2, and 3 are typically related with nuclear power plant and nuclear fuel cycle sites. So the availability is very restricted. On the other side, we have also radiological emergency that are the category 4 for the IAEA that can happen everywhere because they are related with radiological sources that are available more or less everywhere. Industrial source, naturally occurring radioactive material, medical source. It means that they are available in hospital, in industrial facilities, and so on. So we can summarize the radiological and nuclear emergencies because they have the same contaminant, that is a radioactive material, but they have different size and method of dispersion. You can see that radiological accident have a warning time to injury or to provide illness that is from hours to days. The magnitude is local, where local means, let's say, a restricted area from the building up to the city, let's say. And the availability of the source is medium because they are available, as I said, in hospital and industrial facilities, but respect to the chemical, the radiological source are more controlled, let me say. Just to give you an example, chemical can happen with ammonia that we have in our house, with alcohol or with chemical compounds. So the radiological are available, but not available as the chemical. The nuclear have the same contaminant, as I said, but the scales to provide warning and injury are from minutes to hour. The magnitude is bigger. It's city, regional, and we saw also with the nuclear power plant accident like Chernobyl can be also on the scale of more than national, let's say. But the availability is very low, so the probability to make a threat is very low because it's difficult to access to a nuclear power plant without being recognized. So this is the framework in which we are operating. Let me give you a focus on specifically what can be a threat related to radiological and nuclear. We give you just 3 examples of, for example, radiological dispersal device that are devices that cause the purposeful dissemination of radioactive material, but without a nuclear detonation. It can be a spilling out or a purposeful placing of a really strong radioactive source in a metro station or in a crowded area to provide radiation to the people without having their consensus, let me say. We have the orphan source that are sourced in an uncontrolled condition that require to be removed for the public health. So it's something that happened, that the radiological sources that are tracked go out of control, like it happened recently in Australia with the source of cesium that was transported from a site to another site, and when the cargo arrived to the destination, the source was disappeared. And then there are the dirty bombs that are the most dangerous one, but also the one with lower probability is radioactive material that is dispersed using a conventional explosive. Let me spend a few words on this kind of scenario. The real threat is not in the explosion itself, and it's not in the radiological dispersion. Let me specify. The radiological dispersion of radioactive material is dangerous, but the typical amount available to produce a dirty bomb will produce low effect on the public health. The real problem is the spread of panic, the contamination of the area, the loss of trust in the authorities, in the security, and everything that is related to radiological. We know that there is a big lens on it, and Many people don't understand the radiological scaling factor, how much is dangerous or not dangerous. And so this would be the real problem, the panic of the people. In case of one of these accidents, we have to find the measurement quality trade-off. So let me differentiate two different applications that we can work with. We work in both scenarios, but today we have a focus in the emergency measurements. Because when you have an inspection or an investigation, you know that there is a radioactive source, and probably you know also which is the isotopes, and you know where it's located and what is the scenario. So the scenario is well defined. You know the people that are involved. You have time to prepare the sampling and the laboratory analysis, and you need quantitative information as a result. So you have time to plan the intervention that is between hours to days. Totally different is the emergency scenario. In the emergency measurement, you don't know the scenario because maybe an accident is just happened. You don't know how many people are involved, and you must provide an immediate response, a fast response, and you have a really short time to plan intervention. That's why you need to have protocol and trained people to do this kind of measurement. So you have to find the trade-off between the amount and the quality of data, because you need long measurement and really a lot of information to perform a high quality measurement. And this is competing with the time and the speed that is required to provide a really prompt intervention. Let me specify that the quantitative and precise measurement are also performed after the emergency measurement, but later after the site inspection and after the intervention of the prompt responder. So to address this emergency measurement, you need different kind of device, ranging from handheld, that are devices that you can keep in your hand to do the measurement, to backpack measurement, also transportable system like vehicle mountable. Now we have drones to access area that are not easy to access for common person because of, I don't know, debris, or because there is contamination or a fire, I don't know. These different instruments provide counting rate, dose rate. Sometimes they are spectroscopy instruments, so provide radionuclide identification, also neutron counting, and allow to perform characterization directly on site. They have a data storage. These data can be reached back after the mission or streamed directly to a control center. This is really important, so they have a fast communication. Because, you know, the current procedures foresee site inspection, sampling, shipment to the laboratory, preparation, chemical preparation of the sample, and laboratory measurement. But maybe you discover that the sample is not representative of the scenario. So you have to repeat this approach many, many times. With on-site measurement, you can do it directly on site and save a lot of time and provide many information directly with on-site measurement. So in our portfolio, we provide radiological and nuclear instrumentation that are designed to detect and identify the radiological dispersal device, provide the first detection and interception of MORC, that is material out of regulatory control, is the material that is, for example, surveyed by the IAEA, so it's the nuclear fuel or the nuclear waste that can, let's say, disappear, so goes out of the regulatory control, and you have to intercept this kind of smuggling. Characterization of the contaminated area, search and identification of gamma and neutron source, special nuclear material mainly, and also enrichment level estimation and detection, even when the source is shielded or moderated. So let's start with the main device that we are going to present today. Is a Sniper GN, is the most performant gamma and neutron isotope identifier and special nuclear material identifier. Just to give you, let me say a slogan, but just to provide you an immediate idea of the performance. With the Sniper GN, we can detect and also identify in 1 minute 5.6 grams of plutonium placed at 2.5 meters of distance. So now the question is 5.6 grams of plutonium is a big or a small amount? There are publications from the USA Regulation Authority Control that to produce a dirty bomb that will cause, let's say, a real threat, real panic, the amount that you need is more or less 500 grams of plutonium weapon grade. So we are 100 times lower in the size of the source, and we can identify at 2.5 meters of distance. So let's start with the technical part of this presentation, describing the Sniper GN device and the performance. First of all, the Sniper GN, as I said, is a special nuclear material and severe nuclear threat identifier. It's a device that can be controlled remotely through Wi-Fi or can be connected to the USB in the last version that we released. It's equipped with two radiation detectors that I'm going to describe later. Inside there is CAEN nuclear electronic, that is electronic for internal data processing. It's a really performant electronic, high performance electronic that provide the data that I show you in the presentation. Then there is a mini computer for internal data logging, web interface generation, and so on. It's battery powered with rechargeable batteries. You can also switch the batteries and have some spare batteries. And there is a Wi-Fi connection for the data visualization on the tablet, or as I said, you can use a USB connector. So starting with an overview of the available device. Today we are talking of passive detection system used in security control to avoid any interference with the working procedure, because there are also active detection system, but the active detection system require to irradiate the sample that can be a person or a cargo or a backpack. And so it's complicated, and this will for sure interfere with the working procedures. Just imagine a cargo scanning at the border control. You need that the driver will go out of the truck, and you need to irradiate the container, and then you need the results. Here we are talking of passive detection system. This means that we read the radiation emitted by the source. We do not activate the source. The really basic device just provides the gamma counting. Gamma counting means that you start the system, and after a warm-up, you have the count per second of the background. So you know that, for example, 100 count per second is the background here in the office. And then you start to move around. And when you see an area where you have 500 count per second, that is 5 times the background, you will see a pop-up with a warning, and you can start to identify, to check what is the cause of the exceeding of gamma counting. This is really the minimum level of detection system. A benefit can be provided by spectroscopy detector. This means that when you have an exceeding of counting, that there is a contamination probably, and when you press identify, you have the isotope. So you can identify which is the cause of the exceeding of counting, categorizing it and differentiating between norm, that is naturally occurring radioactive material. It means that the background is increased because, I don't know, there is land, grass, plants, I don't know, it's potassium maybe, or rocks of volcanic origin. It can be industrial, so there is a source of industrial origin, and you can understand if it's okay or not. Medical, so if you are in an hospital, it can happen that you have medical waste and is not a threat. Or special nuclear material. Special nuclear material is uranium and plutonium, and is related to nuclear power generation and nuclear waste. And you have to find it just in a nuclear power plant or in a waste repository, not outside. Another plus can be provided by the neutron counting. So again, you count the count per second of neutron on the background is typically around 0, and then 0 or 1 count every 10 seconds. And then if you find an increasing of neutron counting, you know that there is a source, and you know more, because neutrons are emitted only by special nuclear materials. So this is, let's say, the maximum level of alert that you can have. What is not available until today, and now it's available thanks to the Sniper, is the neutron source identification. We use fast neutron through the neutron measurement, not the gamma measurement. Let me explain better what I mean. As I said, in the Sniper, we have two detectors. The first one is a gamma spectroscopy detector, is a cerium bromide, medium high resolution scintillator, and is used to detect, as I said, the gamma. So we perform the gamma counting with this gamma detector, and when there is an exceeding, we perform the peak search, and we are able to identify the gamma isotope, as in a standard read. We do more with the gamma detector. We make a rough estimation of the enrichment level of the special nuclear material, and we enhance the special nuclear material identification, and I show you how. Okay, here we have a plutonium source measured with a common, let's say, read that provide gamma identification, and with the Sniper. You can see that in front of a source of plutonium, the read provides plutonium information because it's able to identify the gamma line coming from plutonium. We are talking about gamma here, but there are also neutron. And so you can see that the Sniper provides you a double confirmation of the plutonium presence, the first one coming from the neutron, and the second one coming from the gamma. We add another benefit, that is the capability to give a rough estimation of the enrichment level by weighting the gamma line emission. So you have plutonium-241 enrichment between 65 and 80% in plutonium-239. So you have also an enrichment level estimation that is really important, for example, with uranium, because if you have natural uranium, it's a mineral, it's a rock, it's natural. But if you have reactor-grade uranium, that's special nuclear material, and maybe the purpose of bringing special reactor-grade uranium is not so good. Then we have a second detector that is a liquid scintillator that performs gamma and neutron counting together. Thanks to the CAEN electronic, we are able, second by second, to provide you the gamma counting, the neutron counting, and their energy, and also the time of arrival in the detector, let's say, the trigger time. This detector and this firmware are the same that are currently implemented in the fast neutron collar, that is a system designed by CAEN for the IAEA on their specification, and is the current standard for the fresh fuel verification. You can see the benefit of having this neutron source identification with neutron. Here we have some plutonium in a cask that is, I don't know, many centimeters of inox steel. So with a common device that provides you neutron counting, you have a warning that neutrons are present. But if you press identify, you do not identify anything because you cannot see the gamma, you have just the neutron. With the Sniper, on the other hand, you have the neutron alarm as in the read, but when you press identify, we are able to identify the source by knowing, let's say, the fingerprint of the neutron. So you can see in the right picture, unknown coming from the gamma, because as the read, we do not detect the gamma coming from plutonium. But with the neutron, we can see the fingerprint of plutonium, and we are able to tell you that plutonium is inside the cask. We have also another benefit that was introduced previously. There is a crosstalk between the two detectors, so the gamma detector do not identify any kind of source. At the same time, the neutron detector is able to identify the plutonium. Then they compare the results, and so the neutron detector, let me say, asks to the gamma detector, how is possible that I identify plutonium and you don't see the gamma emitted by plutonium? Maybe the source is shielded, and that's why we can display plutonium lead shielding. In 1 minute of measurement, this is something that nobody can do. Nobody can identify the plutonium with the neutron, and nobody can tell you that the plutonium is also shielded. We can do this job with different sources. So our algorithm that is patented is trained for different sources, for americium beryllium, americium lithium, californium, plutonium, and uranium. This is a plot of our, at the beginning, let's say, R&D campaign each dot is an identification measurement performed with a single neutron source in a different condition. So you can see, let's focus, for example, on the red area, that is the americium beryllium area. You saw that the dots are spread everywhere. Why? Because we do the measurement with shielded source, naked source, moderated source, masked source. And if the color of the dot match with the color of the box, the identification is correct. This is a two-dimensional projection of a three-dimensional plot. So you have to imagine that the red layer is outside of the screen while all the other are on the screen level. So we can distinguish the red area from the blue and the yellow area because there is a third parameters. The parameters on the axis are the parameter related to the patented algorithm. And this is how we train the algorithm to identify the neutron source. Then we compare the performance of this instrument with the current available standard. And the current standard asks for triggering a gamma alarm in 1 second for a source that provides 500 nanometers. We are able to do it, and we go farther away. We reduce the strength of the source, or we increase the distance, and we are still able to trigger the gamma alarm below 50 nanosievert per hour. That is 1/10 of the standard. So we are able to trigger the gamma alarm in the standard condition and also in a condition that is 1/10 of the standard. To trigger the neutron alarm, you need a 20,000 neutron per second source of californium at 25 centimeter. We are able to trigger the neutron alarm at that distance, and we go farther away to 5 times the standard, so up to 1 meter and 25 centimeter. And also with the shielding, you need moderator in front of the californium. We can detect and identify the californium with this 5 centimeter of polyethylene. So we add more polyethylene and more lead, and we are still able to detect and identify. There is no requirement for the identification of the neutron source through the neutron measurement because, as I say, there is no device on the market that can do it. So the standard, let's say, it's now outdated. Here we have a summary of the best measurement that we made in 4 years of measurement campaign in IAEA, in INEA, that is the National Institute for Energy in Italy, with ENFN, that is the National Institute for Nuclear Physics in Italy, again. So you can see the summary. We are able to identify the plutonium at 2.5 meters of distance. We are able to identify it at 50 centimeters of distance behind 6 centimeters of polyethylene and 5 centimeters of lead. The californium source at 2 meters of distance, and you have the report in the right picture with the double confirmation of plutonium presence when we can detect both gamma and neutron, or the information that is shielded, masked, or moderated when the neutron source is in this condition. Let me spend a few words on the sniper qualification. This device is currently in use in the Italian Navy under the framework of a NATO purchasement. So we do the procedure to have the NATO stock number. The system is has NATO stock number. You see the NATO stock number, it's available. And you can see in the picture the test that we performed with the Army and the Ministry of Defense. You can see the camouflage trousers of the military guys, and you can see the plutonium source behind the lead bricks in front of the sniper to perform laboratory measurement and laboratory test. To do the same measurement currently, if you want to execute simultaneous gamma and neutron identification today, you need at least 3 different measuring systems. The neutron one is the black, let's say, book-shaped device that you can see in front of the small drum. It's a system with helium-free tube inside, and I take the quotation from the paper where there is this publication. It says that you need between 15 to 20 minutes. The weight is 26 kilograms. It works just in laboratory condition. It is designed to identify slightly elevated count rates several hours to obtain an accurate partitioning. The intent is that the data will be provided to experts for later analysis. The threshold mass detection is just for weapon-grade plutonium, 25 grams, so 5 times bigger than the one that we can detect from 2 meters. And the cost of the fission meter is more or less 300,000 dollars, sorry. And then you need also a germanium detector to do the gamma measurement. And you need 12 hours of cooling down and minutes to perform the identification. This means that you need a team of physics experts, nuclear engineer, I don't know, that are available 24/7 to go in the threat area. At the same time, in the area where you detect the threat, you have to isolate the area without creating concerning in the common people. So let's imagine that it happened in an airport. How can you isolate the area, wait the flight from of the expert without creating concerning between the people? This is impossible. With our Sniper GN, you can put it in the backpack, have the tablet in your hand, walk between the people, check in 1 minute, going close to the suspected person, do the measurement, check, and do the identification, and send the information to the person that you need to send it. So maybe your supervisor, let me say. And I want to show you a video with the performance of the system, and I want to comment it with you. I hope you can see the video. And okay, let me move on the part that I want to show you. Okay, this part is the part that I want to comment with you. First of all, here we have a californium. Here we are in our lab, so we have very small source, educational source that I can keep in my hand. That's why the source are so close to the device. You can see that I have a californium source that is a fissional material, so it emits only neutrons. I place it in front of the device, and in 1 second we have the pop-up of the alarm. You can see from the tablet that we have an alarm on the neutron and we don't have any alarm on the gamma. With the common read, here you have just a beep, 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 beep alarm from the neutron, but if you press identify, you don't get anything. With the Sniper GN, you will see now that there is unknown coming from the gamma, because no gamma are in the area, just the background, let me say. But at the same time, we give you californium 252 confidence level 100%. Let's add some obstacle. We put some lead foil in the middle. We change the radiation condition, the environmental condition, not the radiation condition. And again, we have unknown on the gamma and californium lead shielded. Confidence level 80% is a little bit difficult to identify it, but we do it. Then we remove the lead shielding. We put 2 centimeters of polyethylene that is a moderator. It slows down the neutrons. The neutron counting rate is slightly reduced. And you can see that, again, we have unknown on the gamma and californium moderated on the neutron. And let's do the last task. So adding to a neutron source that is moderated, a gamma masking source. It is manganese 54, random source from our laboratory. Now we have alarm on gamma and on neutron, and we have a neutron source that is moderated and masked together. And as you can see, we provide you the information californium, moderated, masked, plus the identification of the manganese 54 that is the masking source. Here we have an example with the famous 5.6 gram of plutonium. This should be, let's say, a dummy smuggler because the source is not shielded. So you have alarm on both gamma and neutron. And at the end of the minute, we have, as I say, the double confirmation of the plutonium presence, one from neutron, one from gamma, with the estimation of the enrichment level. But if the smuggler is smarter than the previous one, he will shield the source with a LED block to shield the gamma, as I said. And here we have an example with another source that is an americium beryllium source. On the left side of the screen, on your left side of the screen, we have the bare source that is in this sort of bar. There is no shielding in front of the source. On the right side, there is a 5 centimeter LED shielding, and you will see that in the end of the measurement, we will provide on one side americium detected by the gamma detector plus americium beryllium source detected by the neutron. On the other side, we do not detect the americium, but we detect that is LED shielded. So you can see americium detected from the gamma, americium beryllium is the special nuclear material. On the right side, unknown because the gamma are shielded, but we tell to the end user that the americium beryllium is LED shielded. And this was the last slide on the Sniper GN. I give you just a quick overview on other device, and then I think it's time for the question. We have many different products that we design for security application, as I say. Some of them are part of the Gammon platform, that is a global measurement platform for nuclear security and safety. We divided this device in 2 blocks: static environmental network that are stationed that we are using to currently upgrade our national environmental network for radiation monitoring. They are fixed station with dosimetry and spectroscopy. And then we have the dynamic monitoring network with drone, vehicle mountable system, and the backpack devices, the Sniper GN. So you have the software that provides you the gamma count rate, the H*10 dose rate, the neutron count rate. You can see the trend of this value. You can see the map. You can see the spectrum. You have the list of the isotope identified on time, directly in real time. And so it's a really easy interface. You can see on this picture, on the top picture, the heat map with the source, and on the lower picture, the spectrum with the list of isotope identified. We use the same electronics and the same system, but just with different housing. And just to give you a quick overview of our device, we have the Gammon Diver, that is an underwater gamma spectroscopy system with real-time activity measurement. So it provides you the activity of the isotope in becquerel per liter. The housing is designed to reach 400 meters of depth or 40 atmospheres. And we have a blanket purchase agreement with the IAEA, and we sold it to the Comsubin, that is the Italian Navy SEALs incursion division. They physically walk on the ground of the sea with this device in their hands and searching for radioactive material. It's let's say a secret, their application, but this is how they are going to use it. This is the Gammon Mobile, the big trolley that you can see in the hand of the military guy. It's a system that is designed to be placed on helicopter or car to perform measurement with very high efficiency detector. It's a 4-liter sodium iodide. This is also NATO qualified with NATO stock number in the same purchase of the Sniper GN, and is currently used by the Italian Navy. Here you can see a picture with different application. You can use it on boat, you can use it in the trunk of the car or on a helicopter. This is the new arrived unit. It's a drone mountable unit together with the drone. So this is the housing of the probe that you can mount on our drone, and having just one connection with the ground, where you have the driving data and also the radiological data. We just successfully concluded the providing of units to the IAEA. And this is a picture of the test that we performed in Brno in an intercomparison with different drone providers. And this is a picture of the offline results. We provide you online data with the software that you saw previously, the same of the Gammon Diver, the same of the Gammon Mobile. Moreover, we are able to provide offline heat map of dose rate, of, for example, in this case was cesium with an estimation of the activity, of uranium, thorium, total activity, and so on. And then I can show you some video if you have further requests. And the last arrived is the Discoverer, is the one that you saw in the comparison between the Sniper. It's a read radionuclide identifying device. It's an handheld. It's equipped with BGO, so it provides gamma counting, H*10 dose rate, neutron counting. We have the finder mode that you can see in the right picture with the trend of counting for gamma and for neutron. There is automatic identification also. So you can see in the picture here, the spectrum with the automatic identification. There is also directionality, a function to understand where the radiation is coming from by rotating on yourself. You can understand if the radiation coming from the right side, from the left side, in front of you, or whatever. The night mode is available. It's IP68, and it can perform spectroscopy up to 1 million count per second, so it's very performant. And we have just concluded an agreement with different customers to provide several units of this device. And we will give you also a demo on this if you are interested, and we have also video on this. This was the last slide, so I stopped the screen sharing and I'm available for the question or for the next step.
Well, thanks a lot, Giacomo. That was a great presentation. Thanks again for your time on this one. I mean, the accuracy and performance of the Sniper GN are truly amazing. I mean, neutron identification, even in difficult condition, in 1 minute is mind-blowing. One question's coming through, and I do have quite a few myself. What accuracy level are you able to achieve for the activity dose rate measurement for cesium-137?
With Sniper, I suppose, is the question.
With Sniper, I suspect, yes.
Okay, let's say currently in the software version, as you can see, we provide count per second. There is no dose rate in the Sniper, because, as I said, the purpose is to identify a threat. And for the moment, we don't provide a dose rate. We are going to release an upgrade of the software version in the next year with also dose rate calculated from the detector, from the scintillator. And so the dose rate, as I said, is not available. The activity is not calculated by the Sniper, but without any kind of product, you can calculate activity directly on site. You need to put the geometry in the middle. And so, for example, in the Gammon Diver, we do it, as I said, because we know that the end user is in the water. So we suppose a source that is dispersed in the volume of water around him. This was the, let's say, the hypothesis.
Thank you, Giacomo. You mentioned that for the identification using the Sniper GN, sorry, to get something with the same accuracy will require more time of measurement and potentially multiple device. What's the secret around the Sniper GN? Is it something to do with the patented algorithm you mentioned? How does it work for the identification of neutron source?
Okay, so I go back to the screen sharing just to use a slide as a support. Let me say, share again. Okay, I hope you can see the screen now. So yes, as you mentioned, the secret is in the patented algorithm, and this axis, the three axes of this plot, are related, as I say, to the neutron counting, neutron energy, and let's say trigger time. In this way, we have trained the algorithm to have the fingerprint of the neutron source for the different and listed neutron source: californium, americium, lithium, americium, beryllium, uranium, and plutonium. And having the neutron information, because the neutron background is close to zero, you need few neutrons, let's say 10 in 1 minute, to provide a correct identification. That's why it's different from the currently available system. Moreover, the currently available system use helium-free tube moderated. It means that they use a thermal neutron, while we use the fast neutron that keep the energy information. So by detecting it and its energy, we are able to recognize the fingerprint, as I said. And once you can identify it from the neutron, you can, let me say, drive the gamma algorithm to search for the specific isotope. So the neutron one is the most sensitive. We have a big efficiency scintillator. You need few neutrons to detect it. In 60 seconds, you have the fingerprint. It's plutonium, it's uranium. And then you tell, let's say, the software tell to the gamma detector, please focus on uranium, please focus on plutonium, and you can find the enrichment level. That is something that you need a lot of time to estimate, for example, with the germanium.
Great performance, isn't it? I mean, it's amazing. I mean, and the capability is the same for shielding and moderation assessment, isn't it?
Yeah, as I explained, there is this intercomparison between the two detectors. One is gamma and neutron sensitive, the other one is just gamma sensitive. So any kind of discrepancy between the detector is due to shielding or source that are masking the neutron source or moderator on the neutron source. For example, with the gamma, we use the gamma detector to perform the gamma identification. At the same time, the neutron detector independently detect the fingerprint of the neutron source. And then when at the beginning of the video, there is a measurement with like 7 gamma source together over the californium source. So the gamma detector finds the 7 gamma source without any kind of problem. Let's say it's pretty standard. And then tell to the neutron detector, remove this contribution because it's due to europium, cesium, cobalt that are not related to the neutron. Once you clean the spectrum, find the fingerprint of the neutron source. It's like cleaning the crime scene and isolating the fingerprint of the guilty guy.
Yes, I understand. We're talking about which we have a question online, typically a CBRNE question, and that specific scenario, I somehow do hope you will never have to run. Someone's asking online. You specified that you can assess 5 grams of plutonium from a distance of 2.5 meters. What would be the maximum distance you would be able to detect 50 kilos of plutonium? That's a lot of plutonium. That yes,
I would like to test it. I want to try to measure 50 kilograms of plutonium. Oh, I don't know. I think there is a physical distance, maximum physical distance for the gamma and the neutron to travel. But let me say we have 5 grams, 50 kilograms is more than 1,000 times greater. So squaring the root, I think that panometrically we can do it at more than 10 meters for sure.
Yes. I think about this question of distance. It's likely. Would you be able? I mean, you can detect from 2.5 meters 5 grams. Let's say if you had 200 grams, could you detect it from the across the street or 100 meters? Do you have any data on that or any experience of how far can you detect a large source away?
Not yet, because we didn't test so big sources. But let me say that if you want to reach a higher sensitivity, you can also couple sniper together. So you can put, for example, 8 of them in a van, coupling all them together. So you have a sensitivity that is the sum of 8 snipers, so 8 times the sensitivity, and you can travel with the van by having a big detector inside. But let me say that for a smuggler is even hard to have 5 gram of plutonium. If we are talking about different applications, so you have a big amount of uranium or plutonium because you are working in a facility. For example, it happened. We are designing, let's say, a redesign of the sniper specifically for some application. For example, you can put it on a tripod, put it in front of a waste drum. Okay, so a drum containing nuclear waste. So maybe score is coming from the reactor. And with this kind of device, by pressing play with a so high activity, you are able to identify the source that are in the cask, even if they are masked with the gamma that is typically correlated to the nuclear waste. And you can easily have a sort of pre-scanning, pre-check of the waste that you are going to characterize with the germanium and with the neutron counting system that are currently available in few sites. They are very big with hundreds of helium-free tubes. So you can do a sort of fast scanning, a quick check on waste container in this case.
So that's something to do with the field of view, isn't it? In general, would you say that the field of view of the sensor is covering a wide area, or is it truly directional?
No, we have in the internal report that then we can share also. We test the directionality because it's required by the standard. We make more or less all the tests required by the standard. And the directionality respect to the detector direction, you have obviously the top sensitivity in front of the detector, but on the opposite side of the detector, where you expect to have the lowest sensitivity, we have still 90% of the detection efficiency respect to the top. So let me say, in front of the detector, you have 100 count per second, the same source, same distance, but on the back side, you still have like 90 count per second. So it's more or less the same. So it's not so directional, but I don't show you properly the software maybe, but there is the search function where you can see the trend of the gamma and on the neutron and also of the alarm threshold on your tablet while you are working with the device in the backpack. This means that if you are walking with the device in the backpack and you see the trend increasing or decreasing, it means that you are approaching or going far away from the source that is near you somewhere around.
All right. Okay. Yes, that does make sense. One last question online here. Does the device record neutron energy? If so, could you get a neutron spectrum to be produced?
The neutron spectrum is produced. You remember the plot with the two lobes where when I say that the same algorithm is used for the IAEA, the upper lobe is neutron spectrum, the lower lobe is gamma spectrum. We make a cut in the middle and we use the two spectrums separately. This is commonly available with CAEN stuff equipped with pulse shape discrimination algorithm. This is not a secret. And we use that neutron spectrum to perform our identification. We have it in our system. And let me say that if for any reason the IAEA would need, for example, the neutron spectrum, we can provide it. But we do not provide it on the common user web interface because we really know the application. We work many times with the end user. And if you have a man that is working, for example, at the border custom control, they want green light, red light. Red light identification, I send it to the supervisor that is a nuclear engineer, and I stop the cargo, and this is my job. Even when we put the gamma spectrum that is useful, you know, if you are an expert, you can understand from the shape of the spectrum if there is something that is not identified, but you can see with a quick lens. Even the gamma spectrum sometimes is required and sometimes is not, because can confuse the end user. The neutron spectrum is something that we read as, let's say, producer, as R&D department, but we do not provide to the end user because it's useless for the end user. For the common user, let me say, then if the end user is the IAA, maybe they would make some analysis on that and we can provide it.
Yes, yes, indeed. Yes, indeed. Well, I've got one quick question. I know that we're running out of time about the Gammon drone. You mentioned the benchmarking through the IAA, actually. Do we have access to those results online? What you showed us on the Gammon drone?
We have some stuff online. We have our internal report of the measurement that we made there. And I think it's under, validation to be published on the CAEN website. You can go on www.caen.it and search for Gammon drone. You have the download area where you can download the datasheet and the whole Gammon family brochure. And if we do some measurement on site, as we made with the Discoverad, we make it available in the download area. So when it's available, we will publish it. Maybe we will make a newsletter. But it was an intercomparison measurement with different providers in Brno in front of IAA. And I think last week, my colleague just came back from Austria where they deliver the units and they were accepted by the IAA.
All right. Sounds good. Sounds good. Well, thanks a lot again. I mean, thanks to Yuri, Giacomo, and Aftab to have taken the time to go through those stories and user cases, and with the very innovative Sniper GN and the Gammon range of technologies that CAEN SyS is offering. Thanks again for sharing your experience, Guy. Much appreciated. And thanks to all of you who have joined us for this webinar. You can get more information on CAEN SyS